In the realm of overhead power transmission, sag refers to the vertical distance between the highest point on a transmission line, typically at the supporting towers, and the lowest point in the middle of the span between those towers. Properly accounting for sag is crucial in the design and upkeep of power lines, as it ensures that the cables do not droop excessively, maintaining safe clearance from the ground and any structures below. Understanding sag is paramount for electrical engineers and technicians involved in power distribution networks. Incorrect sag can lead to severe issues such as power outages, infrastructure damage, and public safety hazards. Factors influencing sag in overhead power lines include temperature, conductor material, tension, and the span length between towers. Power lines sag due to a combination of mechanical forces, conductor properties, and environmental factors. The main reason is gravity acting on the conductor, which causes it to hang in a catenary shape between transmission towers. This sagging is essential to prevent the conductor from being overly stressed by tension. Properly managed sag ensures that the conductor can handle temperature variations, mechanical stress, and environmental conditions without failure. The amount of sag is determined by the balance between tension and weight and must be carefully controlled to maintain line clearance and minimize the risk of contact with trees, structures, or the ground. Effectively managing sag in overhead power lines is crucial for safety, operational efficiency, and the prevention of mechanical failures. Ensuring the correct level of sag allows for adequate clearance between the power lines and the ground or any objects, thereby preventing accidental contact that could cause power outages, fires, or dangerous situations for humans and wildlife. Moreover, optimal sag management reduces line losses and maintains mechanical stress within acceptable limits, thereby extending the lifespan of the power transmission infrastructure. Proper control of sag also ensures that power lines remain functional during adverse weather conditions, such as high winds or heavy ice loads. Types of sag in transmission lines. There are two primary types of sag in power transmission lines. Vertical sag. This is the natural downward drooping of the conductor between two supporting towers and is the most commonly discussed type of sag. Horizontal sag. This occurs due to lateral forces, such as wind, pushing the conductor sideways. Although it receives less attention, horizontal sag is significant, particularly in windy conditions, as it impacts the line's performance. Sag and tension are closely related in the design and operation of overhead transmission lines. Tension refers to the force applied to the conductor to keep it taut between towers, while sag is the vertical displacement of the conductor between the supports. Higher tension reduces sag, but excessive tension can overstress the conductor and the supporting towers. Conversely, too little tension allows excessive sag, leading to ground clearance issues. Engineers calculate the optimal tension to control sag under various conditions, considering the need for reliability, safety, and mechanical strength. Weight of the conductor. The conductor's weight is a key factor that influences sag. Conductors are typically made of aluminum, steel, or copper, with their weight depending on the material and design. Heavier conductors naturally sag more under their own weight, forming a curve between the towers. The weight per unit length of the conductor plays a crucial role in determining the sag, and engineers must balance the conductor's weight with its mechanical and electrical properties to ensure efficient power transmission. Aluminum conductors, steel reinforced ACSR, are commonly used due to their favorable strength-to-weight ratio, reducing sag while maintaining electrical efficiency. Length of the span. The length of the span, or the horizontal distance between two towers, significantly impacts sag. Longer spans create more sag, as the conductor has more room to droop between towers. This relationship is quadratic, meaning that for a given tension, doubling the span length will quadruple the sag. To control sag in long spans, engineers either increase the tension or introduce intermediate towers to shorten the effective span length. In challenging terrains, such as over rivers or valleys, where longer spans are necessary, higher tension conductors or specialized designs are used to minimize sag. Working tensile strength. The working tensile strength of the conductor is the maximum tension it can safely handle without failure. This is a crucial factor in controlling sag, as increasing tension reduces sag, but the tension must remain within safe limits. The conductor's ultimate tensile strength UTS is its breaking point, but in practice, engineers use a lower working tensile strength to ensure longevity and account for factors like thermal expansion, wind loads, and long-term wear. If the tension exceeds this limit, it can cause the conductor to snap or weaken over time, compromising the integrity of the power line. Temperature effects. Temperature variations cause significant changes in conductor length, directly affecting sag. Conductors expand when heated and contract when cooled, meaning that sag increases in hot conditions and decreases in cold conditions. This phenomenon is due to the conductor's thermal expansion properties. When ambient temperatures rise or high electrical currents cause resistive heating, the conductor lengthens, causing more sag. Conversely, in colder conditions, the conductor contracts, reducing sag but increasing tension. Power lines are designed with these temperature variations in mind, ensuring that sag remains within acceptable limits under both hot and cold weather conditions. Stringing and sagging. Stringing refers to the process of installing the conductor between towers, while sagging is the adjustment of tension to achieve the desired sag. During stringing, engineers use specialized tools and techniques to stretch and tension the conductor, setting it to a predetermined sag that accounts for expected operating conditions, including temperature and load variations. Sagging must be carefully controlled during installation to ensure that the conductor does not sag too much or experience excessive tension over time. The initial tension is set based on sag charts or electronic monitoring tools to match the environmental and operational design parameters. Combined effects of wind and ice accumulation can dramatically increase sag, creating additional challenges for transmission line design. High winds apply horizontal forces on the conductor, causing it to sway and oscillate, which increases the apparent sag and puts mechanical stress on the conductor and towers. This wind-induced movement, called galloping, can also lead to conductor clashing, where two conductors collide, potentially causing power outages. Ice buildup, on the other hand, adds extra weight to the conductor, significantly increasing sag and tension. The combined effects of wind and ice pose a serious threat, especially in colder regions, as ice increases the vertical load, and wind exacerbates the lateral forces, both of which must be considered in the design and maintenance of power lines. Preventing excessive sag. Preventing excessive sag involves various strategies. Proper tensioning during installation ensures that the conductor maintains an appropriate sag level under varying conditions. Reducing the distance between support towers' shorter span lengths helps control the amount of sag in long transmission lines. Additionally, using weather-resistant materials, such as conductors with lower thermal expansion coefficients, minimizes the effects of temperature changes on sag. Optimal sag levels in power lines. Industry standards dictate the acceptable range of sag for different types of transmission lines. The National Electrical Safety Code (NESC) provides guidelines on clearance requirements and the minimum acceptable sag to ensure safety and reliability. How sag is measured and monitored. Modern monitoring technologies, such as LiDAR light detection and ranging, are used to measure sag in real time. These systems provide accurate data on the sag of transmission lines, allowing engineers to make adjustments when necessary. Additionally, sag monitoring sensors installed along transmission lines offer continuous data, ensuring that any anomalies are detected early. Sag tension diagrams are graphical representations that show the relationship between tension, sag, and the environmental conditions affecting them. Engineers use these diagrams to determine the best tensioning strategies for power lines based on factors such as temperature and wind speed. Real-world examples of sag failures. There have been several incidents where excessive sag has led to catastrophic failures. One notable case occurred during a winter storm in Canada, where heavy ice accumulation caused significant sag in power lines, resulting in widespread outages. Innovations in sag management. advances in technology have led to improved methods of managing sag. Self-tensioning conductors are now being used in some transmission networks. These conductors adjust their tension automatically based on environmental conditions, reducing the need for manual interventions. Importance of proper sag management. Sag in overhead power transmission lines is a critical factor that can affect the efficiency, safety, and reliability of electrical power distribution. Proper sag management involves calculating and adjusting tension, accounting for environmental factors, and ensuring that the infrastructure is built to withstand changes in temperature, wind, and ice loading. By adhering to industry standards and using modern monitoring techniques, utilities can prevent excessive sag and the risks it poses to the power grid.